The objective of mass spectrometry is to measure the mass-to-charge ratio of a molecule, shattering it into fragments to determine its exact elemental composition. Identifying an unknown compound requires extreme precision. Carbon monoxide and nitrogen gas, for instance, both have a nominal mass of 28 daltons. To distinguish between them, an instrument must measure that mass out to several decimal places. Attaining this level of precision requires overcoming a stubborn physical hurdle. Nature does not provide pristine, uniform particles. Molecules exist in a continuous state of thermal vibration. Before they ever enter a spectrometer, they are bouncing around with random, rapidly shifting starting velocities. If we cannot find a way to control or correct this initial kinetic chaos, the analytical measurements produced by the instrument will be blurred and unusable. The engineering solution to this problem is a class of instruments known as sector analyzers. To achieve mass accuracy down to parts per million, an instrument cannot rely on a single physical filter. It must independently separate ions by their momentum and by their kinetic energy. This dual filter approach is known as double focusing. This schematic details the Near-Johnson geometry, an architectural arrangement where a sweeping electric sector and a magnetic sector operate in tight sequence. To understand how these components work in concert, we first have to build a single focusing magnetic spectrometer and identify the specific physical bottleneck that necessitates high-resolution design. This diagram illustrates an electron impact ionization chamber. A beam of high-energy electrons bombards the sample, creating positive ions. These ions are pushed by a repeller plate, then drawn through a massive potential difference, an accelerating voltage applied across a series of plates. The kinetic energy gained by each accelerated ion is defined by this simple equation. It equals its charge, E, multiplied by the applied voltage, V. But there is a hidden mathematical assumption here. It assumes every ion starts perfectly at rest. If this idealized state were true, isolating different masses would be a straightforward one-step calculation. The accelerated ion beam now leaves the source and enters a perpendicular magnetic field. In this vector model, the magnetic field exerts an inward Lorentz force on the moving charges, bending the beam into a circular arc. For a stable trajectory, this inward magnetic force is balanced perfectly by the outward-pointing centrifugal force of the ion. This textbook excerpt proves this equilibrium, equating the forces in equation 11.9. By substituting velocity with kinetic energy terms, we get equation 11.13. The mass-to-charge ratio equals the magnetic field squared times the radius squared, divided by twice the voltage. By holding the magnetic field strength and flight radius constant, an analyst sweeps the accelerating voltage, selectively steering one specific mass to the detector. This mathematical model hinges entirely on the assumption that all ions enter the acceleration phase from a standstill. But physical reality is messier. Gas molecules possess initial thermal energy, exhibiting highly variable, chaotic speeds right up until the flash of ionization. Because their initial velocities vary, the final kinetic energies of the ions entering the magnetic sector also vary. This occurs even among ions possessing the exact same mass. In this magnetic field simulation, particles share the same mass with varying kinetic energies color-coded. Higher energy ions carry more momentum, carving a wider radius, while slower ions carve a tighter curve. They strike the detector as a broad band, not a sharp line. A purely magnetic sector does not isolate mass, it isolates momentum. Varying kinetic energy broadens the resulting spectral peaks, capping the mass-resolving power of a single focusing instrument at roughly 2000. To achieve higher resolutions, we must introduce a secondary filter before the magnet, one that ignores mass entirely and separates ions only by their kinetic energy. This is the electrostatic sector. It consists of two curved plates that create a repelling outer wall and an attracting inner wall. Our multi-energy beam enters the gap here. The electric field inside applies a force that bends the ion trajectories. Crucially, this curve depends solely on the distribution of their kinetic energies. The highest energy ions plow outward into the repelling wall, while the lowest energy ions are pulled inward. Both are neutralized. Only a narrow beam of ions, all sharing a uniform kinetic energy, successfully navigates the curve and exits the slit. The electrostatic sector normalizes the beam. It forces the chaotic physical reality of the ions to match the idealized mathematical assumptions we required at the start. Returning to the near-Johnson geometry, we can see the complete architectural implementation. The electrostatic sector is positioned immediately before the magnetic sector. The beam accelerates from the source, sheds its kinetic energy variations in the electric sector, and enters the magnetic sector uniformly. Because the kinetic energy spread has been eliminated, the magnetic field's momentum separation now correlates with the actual mass-to-charge ratio. This double-focusing geometry provides an exceptional degree of ion beam focusing, elevating the instrument's mass-resolving power from 2,000 to over 100,000. By using opposing physical fields to filter for the initial energy of the ions, designers created an instrument capable of resolving the exact masses of molecules that share the same nominal weight.